Okay, dear students, now I am discussing about Gauss law in electrostatics. What is the statement of Gauss law in electrostatic? Electric flux through a closed surface in a free space is equal to 1 by epsilon naught times total charge enclosed by the surface. Consider any closed surface containing charges. Okay? Closed surface containing charged body is chosen for the applications of Gauss law. Any closed surface containing a charged body is the chosen for applications of Gauss law. Gauss law is applicable by take the closed surface in a charged body. What is the statement of Gauss law? Statement: electric flux through a closed surface. Electric flux through a closed surface. Electric flux through a closed surface in a free space or vacuum. Free space or vacuum is equal to 1 by epsilon naught times total charge enclosed by the surface. Total charge enclosed by the surface is called Gauss law. According to this statement, the electric flux through a or over a closed surface phi must be equals to 1 by epsilon naught times total charge Q enclosed by the closed surface. According to the statement, phi is equal to 1 by epsilon naught times Q. Where epsilon naught is the permittivity of the free space, Q is the total charge enclosed by the closed surface. What is the total charge enclosed by the closed surface? For example, this is one of the sphere of radius r. Sphere of radius r, it enclosed by the charge Q. The flux through this sphere is phi is equal to 1 by epsilon naught times total charge. Suppose this sphere enclosed by the charges, two charges, minus charge. What is the flux through this closed surface? Plus Q and minus Q cancel. Net flux through the surface becoming 0. Okay? Closed surface enclosed by dipoles. Net flux through the surface becoming 0 according to Gauss law. Any closed surface enclosed by the dipoles. For example, the magnetic dipole. Okay? Gauss law in magnetism is magnetic field lines enclosed by the closed surface or flux enclosed by the closed surface must be 0 because of magnet is always exist in a dipoles. Similarly, the closed surface contain minus and plus Q. Net flux through the surface becoming 0 according to the Gauss law. Net flux means total charge enclosed by the closed surface. It not depend on the charge on the outside of the closed surface. It only depend on charges enclosed by inside the closed surface. Next, verification or proof of Gauss law. Verification or proof of Gauss law. Verification or proof of Gauss law. How to verify? We take considering sphere of radius r. Considering small sphere of radius r. Small sphere of radius r when charge Q is enclosed at the center of the sphere. Charge Q is enclosed at the center of the sphere O. The whole sphere is divided into small area elements. Delta S. Whole sphere is divided into small area element delta S. This is the delta S. This is the electric field at point P. Electric field at point P. Whole sphere is divided into small area element. What is the electric flux through this area element is given by electric flux through area element delta S is flux phi is equal to summation of E dot delta S. Summation of E dot delta S. Delta S be the area vectors. And the direction of electric field vector and area vector are in same directions in a closed space. And the area vector is always drawn normal to the surface. Small element, area element, normal to the area element. And this is the area vector. Direction of area vector and E are in same directions, and the angle between E and delta S is 0 degree. According to the dot product of two vectors, E delta S cos 0, angle between E and delta S is 0 degree. The cos 0 is 1. Cos 0 is 1, where flux through the area element is given by pi is equal to E into delta S. Flux through the area element is given by pi is equal to E into delta S, where E is taken from the summation. E is taken out from the summation. It is the summation of delta S. This is take equation 1. Electric field due to this Q at point P outside the sphere is given by 1 by 4 pi epsilon naught Q by R square. This is the electric field due to this positive charge at point P into summation of delta S. This is the equation 2. Where summation of delta S is the total area of the sphere. Summation of delta S must be equal to total area of the sphere. What is the area of the sphere is 4 pi R square. Substitute this 4 pi R square value in 2. We get pi is equal to 1 by 4 pi epsilon naught Q by R square into 4 pi square. 4 pi get cancelled, R square get cancelled, where electric flux through the closed surface must be equal to 1 by epsilon naught times total charge enclosed by the surface, according to the Gauss law. This is the proof of Gauss law by using a sphere of radius R. It enclosed by the charge Q. This is the verification or proof of Gauss law. According to Gauss law, electric flux over the closed surface in a free space must be equal to 1 by epsilon naught times total charge enclosed by the surface. Okay. Next, applications of Gauss law. Applications of Gauss law. Applications of Gauss law. Three applications of Gauss law. First application, electric field due to long straight uniformly positively charged conducting wire. This is the first applications of Gauss law. What is the first application of Gauss law? Electric field due to long straight uniformly positively charged conducting wire. It takes one of the infinite length of the conducting wire. The charges are uniformly distributed like this. Positive charges are uniformly distributed throughout the length of the wire. Consider two length elements in this wire. P1 and P2 be the two length elements. Consider P1 and P2 be the two length elements. Electric field due to P1 is taken along these directions, E1. Similarly, electric field due to this P2 is taken along these directions, E2. The resultant electric field is along the curved surface or radial distance or at point P. This is the resultant electric field at point P, and in the radial distance from the center of the wire. And the resultant electric field is always in radial distance. It is the electric field due to P1 length element, electric field due to P2 element. This is the resultant electric field, and the combined effect of electric field due to P1 and P2 along radial distance. Andre any charged conducting wire is taken, the electric field is always normal to the surface in the radial distance. You prove this how much electric field in radial distance by consider imaginary cylindrical Gaussian surface to the infinite length of the wire. Consider imaginary cylindrical Gaussian surface. To calculate the electric field due to this length element, consider imaginary cylindrical Gaussian surface. This is the imaginary cylindrical Gaussian surface. The electric field is always at point P in radial distance. You know, electric field due to this length, this conducting wire is always in radial distance. But calculate the electric field at point P by using Gauss law. How to calculate electric field at this point P? The electric field due to two end face of the cylinder, imaginary cylinder is 0 because of angle between E and delta S is 90 degree. Angle between the E and delta S is 90 degree. Electric field is always normal to the surface. But in the end faces of the cylinder, the electric flux through the end face of the cylinder is 0 because of angle between the E and delta S is 0. Only flux crosses the curved surface of the cylinder. Flux crosses the curved surface of the cylinder. Curved surface of cylinder. Flux crosses the only curved surface of the cylinder in radial distance. End face of the cylinder, flux through the end faces of the cylinder is 0 because of angle between the E and DS is 0 degree. The angle between the E and DS cos 90 is flux becoming 0 at the two end face of the cylinder. But along the radial directions, in radial directions, angle between E and delta S is 0 degree. Andre angle between the E and delta S in radial distance. Consider one of the closed surface. In this point, this is the delta S, is the area element. The angle between the E and DS along in this direction is 0 degree. According to definitions of Gauss law, flux through the closed surface is equal to 1 by epsilon naught times total charge enclosed by the closed surface. What is the charge enclosed by this closed surface? Is equal to lambda into L. According to linear charge density, lambda is equal to charge by length. The total charge enclosed by this delta S is Q into lambda into L. Put this value in equation 1. Phi is equal to lambda L by epsilon naught. This is the equation 2. According to definition of electric flux, E is equal to summation of E dot delta S is equal to lambda L by epsilon naught. In radial distance or curved surface of the cylinder, angle between E and delta S is 0 degree. In curved surface, angle between E and delta S. E is the electric field vector, delta S is the area vectors. angle between the area vector and electric field vector is 0 degree. We put the value in equation 3. In equation 3, put where summation of E into delta S cos 0 is equal to lambda L by epsilon naught. Where cos 0 value is 1, E is taken from the summation, delta S is equal to lambda L by epsilon naught. Lambda L by epsilon naught. Where summation of delta S is the total area of the curved surface of the cylinder. Total area of the cylinder. Delta S is equal to 2 pi RL. This is the area of the cylindrical surface. Area of cylinder or cylindrical surface. This is equation 4. Substitute this value in 4. Delta S value in 4, E into 2 pi RL is equal to lambda L by epsilon naught. L get cancelled. Electric field due to infinite length of the conducting wire at point P is in curved surface is lambda by 2 pi R into epsilon naught. This is the expression for electric field due to uniformly positively charged conducting wire at point P in the curved surface. The uniformly charged positively charged conducting wire at the end face of the cylinder is electric flux through the end face of the cylinder is 0. Electric flux 0, field is also end faces of the cylinder is 0. The net field along the curved surface in radial distance. This is the first applications of Gauss law. E is equal to lambda by 2 pi R into epsilon naught. Next, second applications. Electric field due to uniformly charged plane sheet. Second applications. Electric field due to uniformly charged plane sheet. Uniformly charged plane sheet. Electric field due to uniformly charged plane sheet. Consider plane sheet. Plane sheet consider. This is the one of the plane sheet. The charges are uniformly distributed throughout the plane sheet. Uniformly positively charged plane sheet. The electric field is always normal to the surface of the charged body. Any charged plane sheet is andre electric field is always normal to the surface. To calculate the electric field due to this plane sheet is by using, consider imaginary cylindrical surface. Imaginary cylindrical Gaussian surface. Imaginary cylindrical Gaussian surface. In an imaginary cylindrical Gaussian surface, electric field due to two end face of the cylinder, the electric field is always normal to the uniformly charged plane sheet. Along the curved surface, electric field is 0 along the curved surface because of electric field is perpendicular to the area element. Net electric field due to two end faces of the cylinder. In uniformly charged plane sheet, electric field due to curved surface of the cylindrical surface is 0. Electric field due to this imaginary cylindrical surface is 0. In uniformly charged plane sheet, electric field due to plane sheet in imaginary curved surface of the cylinder is 0. Curved surface of cylinder is 0. Only flux crosses to end face of the cylinder. End face of cylinder. Flux crosses only to end face of the cylinder is phi is equal to E into A plus E into A. This is equation 1. Along the curved surface of the cylinder is flux is 0. There is no flux across the curved surface. Electric field due to curved surface of the cylinder is 0. Because of the angle between the E and delta S in this region is 90 degree. The net flux crosses the two end face of the cylinder. Net flux crosses two end face of the cylinder is given by phi equals to EA. One end face of the flux plus another end face of the flux. The net flux through the curved surface is 0. Field is also 0. According to the Gauss law, phi is equal to Q by epsilon naught. This is the equation 2. Q be the charge enclosed by the closed surface. Or charge enclosed by the plane sheet is given by Q is equal to sigma into delta S. Or sigma into A, total plane sheet. Sigma into A. Substitute this Q value and phi value. Q and phi value into, we get electric field due to uniformly charged plane sheet. Let's substitute this value. Sigma into A is equal to sigma A divided by epsilon naught. Flux is equal to 2EA. EA plus EA, 2EA is equal to sigma A by epsilon naught. A get cancelled. E is equal to sigma by 2 epsilon naught. This is the expression for electric field due to uniformly charged thin plane sheet. Sigma is the surface charge density, where epsilon naught is the permittivity of the free space. This is the uniformly charged plane sheet. The end faces are only flux enclosed by two end faces of the cylinder. Along the curved surface of the cylinder is net electric flux through the curved surface is 0. Electric field in the curved surface is also 0. Because of angle between the electric field vector and area element is 90 degree. Net flux through the surface is 0 along the curved surface. Only flux crosses two end face of the cylinder in the case of uniformly charged plane sheet. This is the expression for electric field due to uniformly charged plane sheet is sigma by 2 epsilon naught. Sigma is called surface charge density and charge per unit area of the surface. Epsilon naught is the permittivity of the free space. Next, third applications of Gauss law. Third application. Electric field due to uniformly charged spherical conducting cell. Third application. Electric field due to uniformly charged spherical conducting cell. Spherical conducting cell. First A, outside the spherical conductor. First, electric field due to electric field due to spherical conducting cell. Point P outside the spherical conducting cell. Outside the spherical conducting cell. Outside the spherical conducting cell. Electric field due to spherical conducting cell. Point P is outside the cell. So outside the spherical conducting cell. We consider spherical conducting cell of radius r. Consider a spherical conducting cell. This is one of the spherical conducting cell. This is one of the spherical conducting cell. The charges are uniformly distributed like this. Positively charged spherical conducting cell of radius capital R. We can calculate the electric field due to this spherical conducting cell at point P lies outside the sphere. Outside the sphere. Point P lies outside the sphere. Consider imaginary spherical Gaussian surface. To calculate the electric field due to cell, consider imaginary spherical Gaussian surface to the spherical conducting cell. This is an imaginary spherical Gaussian surface. Consider imaginary spherical Gaussian surface to the spherical conducting cell to calculate the electric field at point P due to spherical conducting cell. How it calculate? We consider one of the closed surface in the spherical conducting cell. In the spherical Gaussian surface, consider closed surface delta S be the small closed surface. Delta S be the small closed surface. The electric flux through this closed surface. Electric flux through closed surface delta S. Small closed surface delta S is phi is equal to summation of E dot delta S. Phi is equal to E dot delta S. First you consider the imaginary spherical Gaussian surface to the spherical conducting cell. Then consider small closed surface in the Gaussian surface is delta S. The electric flux through the closed surface delta S is phi is equal to E into delta S. According to Gauss law, flux through a closed surface must be equal to 1 by epsilon naught times total charge enclosed by the surface. Total charge enclosed by the surface. Substitute the flux value in 1. Phi is equal to summation of E dot delta S in 1, where E dot delta S is equal to Q by epsilon naught. Where according to the dot product of two vectors, E dot delta S is equal to E delta S into cosine of the angle between the vectors. It is the product of their magnitudes and cosine of the angle between the vectors. E delta S cos theta is equal to Q by epsilon naught, where angle between the delta S and E in this direction is 0 degree. And the angle between electric field vector and area vectors. This is the delta S is the area element area element, area vector is perpendicular to the area element. Area vector is always drawn perpendicular to the area elements. And angle between the electric field vector and area vector is 0 degree. The angle between E and delta S is 0 degree. Angle between E and delta S is 0 degree. Angle between E and delta S is 0 degree. 0 degree ಆದಾಗ ಏನಾಗುತ್ತೆ summation of E delta S cos 0 is equal to Q by epsilon naught. Where cos 0 value is 1. We take E is taken from the summation. Sum of the delta S is equal to Q by epsilon naught. Sum of delta S, it is only one area element. This Gaussian surface enclosed by large number of delta S. Gaussian surface contains large number of delta S like this. Summation of all this area element is equal to area of the spherical Gaussian surface. Where delta S is equal to summation of delta S is equal to area of the spherical Gaussian surface is 4 pi r square. Summation of delta S must be equal to area of the spherical Gaussian surface. Substitute this delta S value. This will take equation 2. Substitute this delta S value in equation 2 to get